So first thing you decide which is easy to define is you define things that are nicely called, sometimes mathematicians use sensible words, very rare, but this is an example. Wandering point. So aperiodic motion could have a following property. If I started in a neighborhood of some point x at time 0, so this is now a little cloud, a little finite set, like things that I drew here. If I start in a neighborhood, and now I apply my law to this point, to this trajectory, I started here at x, but I started in a little neighborhood. And then for a while, I'm in this neighborhood because it's continuity and I have to get out. So there is an exit time. And now I look at all time afterwards, all t later than that. And if I can establish that x t never returns to the set, then the point is wandering. So it says, there are things, there is a student in my classroom, he exits, he wanders around Georgia Tech, he wanders out Atlanta, and he gets to Mexico and goes on, but never returns to my classroom. So that's a wandering student. Or by exclusion, and that's much harder to define, the ones which are not wandering, a non-wandering set. So we are almost here with Babylonians, but we are not demanding. We say, well, let's relax it. I mean, expecting that I exactly come back, that's really crazy, especially if I have any noise or any imperfection in law. But even for deterministic law, that's very hard. So what you do is you kick out all wanderers, all the dreamers. We don't want them at Georgia Tech. We want only drones, so wanderers go out. I pull out a capital Greek letter just because we are running out of letters. Call this set omega. So this is what remains, so you start everybody, the semester starts, and the non-wanderers are the ones who are still at the end of not this semester, but infinitely many years afterwards. They never leave. And that goes to, the key idea of theory of chaotic deterministic systems, again, due to Henri Poincaré, which is notion of recurrence, which you might have encountered in your statistical mechanics or your mechanics courses if they were top-notch. So that says that if I have a neighborhood of X, and if I, start running around, I leave that neighborhood, but then I discover there are intervals in time there are times when I come back, and these are little intervals because it's a finite neighborhood. I enter, it takes me a while to get out. And it's a simple thing to convince yourself that, there is an integer case says, this is the 7th time I've come back. But then you'll convince yourself there are many of those returns. And then you're convinced that if you return once, you will return infinitely many times. So that's a set, which is a subset of all possible things in my state space. So there are thousands of students, particles, etc., large, but the ones that keep coming back and returning, they're the recurrent set. And this is now a very powerful motion that replaces what Babylonians thought about when they thought about the firmament. You don't have to come exactly back if you're in some asteroid belt. You just have to come close enough. And that's a powerful thing. So now that you have this notion of non-wandering sets, some of them are very weird. So for example, when nobody does it anymore, but if you're lucky, there is a museum in, I forget, Charlottesville or someplace, a pinball museum. So there are machines. So basically what pinballs used to be, there were little machines where, human size, where you would use a flipper to send a ball, the ball would bounce around, and then you would do your things, try to keep it as long as you can, and it would eventually fall out. So the set of all balls that stay infinite time in the flipper, that's a non-wandering set. And the set of balls that stay there for some finite time, they provide kind of covering. The real set is smaller than that, but that gives you an intuition that all possible states, very few might be in non-wandering set. So that set might be much lower dimensionality than your infinite dimensional world that you started with, let's say, of fluids.